So hi to everybody. Well, not everybody, clearly, and thank you guys for being here. I definitely want to give you guys a shout out and give you the opportunity to ask questions, or if you came to the session hoping to see some problems work from like the book chapter or something like that. We certainly interrupt me anytime with questions. Does anyone have anything they want to see at the start or any questions? Okay, and also definitely let me know if there's any technical issues about the screen sharing or the audio or anything. So I'm pointing out the YouTube channel. Clearly this unit, chapter 13, there's already an hour and a half worth of stuff to watch. So, and the quiz will be like last week, posted around noon tomorrow and due around noon Saturday. So let me get this. Oh, that's not what I wanted to bring up. So so for folks that haven't yet watched either of the videos or participated in the Zoom session like you guys are, they've got, you know, an hour and a half of stuff to try to get through prior to looking at the quiz, or at the same time, all at once at the end, which isn't really a great strategy. So again, shout out to you guys for being here. Now, I just brought up where I left off, I guess, in chapter 13. The last video was on aromatic stuff. So this was the last video, just sort of scrolling through, and we sort of ended on naming of aromatic compounds when they have things stuck on them, like bromines, methyl groups, OHs, and things like that. So I just wanted to remind us where we left off, kind of. So today's Zoom session, which we're in right now, and I'll put the reminder up there. Quiz, chapter 13. Tomorrow, noon, 24-hour. And then start to look for postings for chapter 14 topics. And I figure at the end of this session, I'm going to sort of segue into what chapter 14 will be about. If I think I'll have time. This window. Okay, there we go. So back to what we've been doing, alkenes and alkynes. We went over structure and bonding, nomenclature or naming, you know, to pentene or whatever it is. Double bond, a pentane, but with a double bond at carbon 2, so it's a 2-pentene, things like that. Reactions, and almost, I think all of those were ways to add atoms to the double bond. So the way I would rank these is, you know, highly ranked, you know, the naming, it's attractive, and the book overemphasizes it, in my opinion. It's systematic, people kind of like that, you know, but there isn't, that's not the chemistry of stuff, right? You know, it's how we navigate the chemistry in some ways, but so I would rank structure and bonding, and structure and bonding clearly relates to how things react. So that's the overall concept. Same with benzene type compounds that we just started covering. The structure and bonding of benzene important. They're highly stable, stability. Nomenclature, again, you know, we want a working knowledge of it, but we don't want to go crazy with it. And then the reactions, except we haven't done any reactions of benzene type compounds. What we're going to look at toward the end of this session is, maybe a better way to say it, reactions of what is stuck on the benzene ring because the benzene ring itself is stable, and meaning far less reactive. But what's stuck on side chains, for example, or side functional groups, I'll call them side chains. Yeah, maybe I don't like that. Side groups, not because it doesn't have to be a chain. Those react, but they react in the same way as the things that we're going to spend the rest of the quarter basically marching through, which is, how does an alcohol react? How does a ketone react? How does a ether or a thiol or an amine react? Those are the things that are going to be stuck on the stable benzene ring, which for the most part is going to stay unreactive. So the little glimpse of where things are going with all of this. I feel like the reactions of alkenes need a good amount of time, and I have spent a good amount of time on them, but I think it's worth spending more time today. And tips on figuring out how these reactions go. So, clearly you're going to see a bunch on the quiz. Markovnikov's rule. So I'm not a big rule person. You can memorize Markovnikov's rule, however, and which I am consistently unable to do after teaching organic chemistry for 18 years, believe it or not. But what I remember is the mechanism of the reactions, which I feel is far more reliable, and understanding which carbocation is more stable. So allows me to basically know Markovnikov's rule because that's what it's based on. Each carbon of the double bond, the carbon-carbon double bond, forms a new bond. And so clearly the double bond will be gone in the end. And hopefully you've worked enough problems, practice problems in the book and so on, to realize that when you add, say, HBr to a double bond, you get the H attaching to one of the carbons, the bromine attaching to the other carbon, but the double bond will be gone because it's the electrons of the double bond that are needed to make those new bonds. That's a super important point. Being able to see alternate possibilities. That's really what Markovnikov's rule in this part is about. Because if you have a double bond with the two carbons, the hydrogen can go to one and the bromine to the other, or vice versa. So how do you know? And a lot of that is seeing different possibilities. And if we back up from that, when you think about it, isn't that really like every scholarly activity? Looking for different possibilities. Instead of just everything going in a straight line, the world doesn't really work that way. It's like it could go this way, it could go this way, this way, especially in science too. So. So I have some more examples set up to go through. And I'll go through them real slow, but definitely feel free to interrupt with any questions so far. Is there anything right now, though, before I get started on this? Okay, this compound, I like this example because we should be able to predict the product and realize that the reaction is going to take place at the alkene. We do see this other double bond here, right? But that's not an alkene. This functional group is a carboxylic acid. And we want to always still remember to be able to identify functional groups, carboxylic acid. So this unit's on alkenes, and presumably all these reactions are alkene reactions. And so the carboxylic acid is not going to react, won't react. It doesn't react because it's a carboxylic acid. It won't react because of the nature of the electrons around this carboxylic acid is so different from the nature of the electrons on the alkene, which the ones to focus on are, well, either of those two lines, because there's a pair of electrons there that are different from the other pair of electrons, which I went into in detail. So we should be able to predict that one of the bromines of the reagent is going to attach to one of these carbons here, and the other one's going to attach to the other carbon. And in the process, these extra electrons are going to be used up to make those new bonds. So pretty easily we can predict and by the way, with things like this, you could number carbons to make sure you don't lose them in the process. That's a good tip for keeping track. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And I have to do this sort of numbering a lot. So put a bromine on 6 and a bromine on 5. And they tend to add on opposite sides like this, except in this case, it won't matter because the whole thing can rotate around. If it was a double bond on a ring, one would end up being pointed up and the other pointed down. So this example essentially reviews where the bromines go. It points out that the double bond is gone because those electrons are used up. The 2 electrons of the double bond end up here and here. And the other electron each of these new covalent bonds are contributed by bromine. Remember, covalent bonds are nothing but more than the sharing of electrons between atoms. Carbon there, carbon there. And the other thing that this example shows is that reactions can be specific as far as if there's multiple functional groups in a molecule, one will react and the other not. If, in fact, this carboxylic acid was reactive with bromine, you wouldn't be able to do this reaction. You would have to do something to this carboxylic acid to make it not react, and then undo it later after you did your reaction over here, which is actually a widely used method called protecting groups. You can create a protecting group here on the carboxylic acid, do your reaction on the alkene, and then deprotect the carboxylic acid, and then continue forward in your scheme. I was just covering that in my most advanced organic class, Organic 3, this quarter. So bromination was one of the 4 reactions we learned. Adding water across the double bond was another one, hydration. Hydrating. Gotta stay hydrated. So looking at the double bond, we see that there's different possibilities in this case. So up to my bullet item list, seeing different possibilities. And we know that H is going to bond to one of the carbons and OH to the other. But then again, it could be the other way around. So I encourage people to, rather than just sitting there thinking about which one it's going to be, just draw both of them. If you remember Markovnikov's rule, you would say to yourself at this point, well, the H is going to add to, well, see, I already forgot Markovnikov's rule. The H adds to the carbon with that already has more H's, right? But let's draw both possibilities instead. So let me do one other thing here. So I'm going to put this carbon here, double bond, carbon, and let's draw this out sort of like that. And so I already messed up here. Am I going to be able to do that? Okay, so you're going to get one possibility where, here, I'll do the colors to make it clear. Okay, H adds there, OH adds there. Back on track here. So, and the other possibility, H adds here, OH adds here. And then you can see Markovnikov's rule. The H adds to the carbon that has more H's already to begin with. And so that's this one. So this one's the right answer. And the net reaction, addition of water to each carbon across the double bond, you would say, H to one, OH to the other. So keep in mind, the only way I knew at this present time in this example that this was the right answer was to remember Markovnikov's rule, and you saw me struggle to remember it. Imagine all the reactions and all the rules if you were to do it that way. It would be far too much to remember. So later, in a few minutes, I'll show how this actually works. And you can decide for yourselves if you want to remember it that way or remember it just Markovnikov's rule. Which is really, I'm mainly just requiring that, I'll say. So the other reaction to review, hydrogenation. Adding of hydrogen. So H2 is a molecule of hydrogen comprised of 2 hydrogen atoms. And if we remember how this reaction goes, hydrogen is going to add to each carbon of the double bond. So this one's super easy. Notice this time I drew out all the atoms to begin with. You can go back and forth for a while, but usually the line drawings that we do are so much faster to draw. So hydrogen adds there, hydrogen adds there, the double bond is gone. And that's it. Since it's symmetric, right? Each one's a hydrogen, it doesn't matter that this carbon here has different things attached than this carbon here. So it's not a case for Markovnikov's rule. You're adding the same thing to each carbon. So it doesn't matter if it's this way or this way. The other thing that I'll just remind people of, this is an unsaturation. So this is unsaturated. And this is saturated. So those terms, unsaturated and saturated, refer to, you could add the word with hydrogens. So with or without hydrogens, you know. So saturated, it's saturated with hydrogens. It's unsaturated, well, due to the removal or absence of hydrogens. Finally, we did go into the details of this one. It still goes according to Markovnikov's rule. So this is the same molecule as I used above. And we remember then that according to Markovnikov's rule, the hydrogen here will go to the carbon that is the CH2. It already has more hydrogens. This carbon doesn't have any hydrogen. The chlorine will end up there. And so according to Markovnikov's rule, we're going to end up with H. And you know, that's the right answer. So we did break this apart into steps. And the steps we did, let me just, were that the reactive electrons, always comes back to electrons, will form a bond to hydrogen, to the proton of the hydrogen atom. A hydrogen atom is nothing but a proton and an electron. The electron of the hydrogen atom is there, being shared. The H symbol then really just represents a proton, a subatomic particle. Forms a bond. Since hydrogen can't form two bonds, this bond breaks. Bond breaks. That leads to well, here, I'll do this. There's the new bond to hydrogen. And then the other feature of this that's really pretty important is that you get a plus charge there. This carbon right here had 4 bonds with all those electrons around it. Now it only has 3 bonds, so it's deficient in electrons, meaning it has less negatives, and so it's a positive. What happened to the chlorine? The chlorine floated off with extra electrons. So the chlorine is sitting there as a minus because it has extra electrons. And then the final step is just one more bond forms. To get to right there. So it's really not that much more, but that little bit helps us understand Markovnikov's rule better, because when the hydrogen adds to this carbon, it leaves a plus charge here. And we learned that plus charges prefer to be on carbons that are tertiary like this. This is a tertiary carbon, meaning it's a carbon with 3 other carbons attached and no hydrogens. If the plus charge was up here, where I'm pointing, it would be a plus with a carbon that's got 2 hydrogens on it. That's a primary carbon and basically completely unstable. It basically can't exist. It's so unstable. And so we learned carbocation stability. tertiary is more stable than secondary, is more stable than primary. And we're going to see this again, this concept at least of stability of charges. Stability of charges, huge in organic chemistry. Because so many, virtually every reaction results in the formation of some kind of charge somewhere. And if there's an alternate possibility of where that charge could be, all you got to do is determine which one's more stable. And to me, this is a lot easier to remember. Just tertiary, secondary, primary. So how much is understood of what's going on? This would be a good test, because what we saw up here with adding water, we could start to think, well, is this really that different from HCl? Kind of not, right? We started with the same molecule, and the H ended up adding to this carbon, and OH adding to this carbon, and this did not form. So it really looks a lot the same to me. So let's see if we can use what we've learned to apply to things we haven't seen before. Which again, I mean, when you think about that, it's like, isn't that kind of what we're striving for in general for everything? If you could only perform and accomplish things that you've done before, okay. So if you follow this, but this is pretty different from what we, at first it looks different. So here's our alkene. We know that electrons of the double bond can go and form a new bond. It would be helpful here to draw in the implied hydrogens. Very helpful. And so these electrons, if we remind ourselves of Markovnikov's rule, for example, or if we just say, where's the plus charge going to go, which is those two things are the same thing. Markovnikov's rules would say that the hydrogen that this double bond bonds to first is going to go to this carbon. So we can say, where's it going to get a hydrogen from? Acid. Where does this acid come from? That's the reaction conditions of hydration. And I pointed that out, oops. From, I'm positive I pointed that out before. So hydronium ion, so bond forms. Hydrogen can't form more than one bond, so these electrons go to the plus charge oxygen. Electrons are like, we're negative and we want to go positive. That leaves this. So if I draw the implied hydrogens in here, we have a new one added on the end, and there's a hydrogen there. And so this carbon that used to have 4 bonds now only has 3, and it's electron deficient. And we're back exactly to here. At first it looks a little different because of the ring and all that. This is exactly the same as where we're at right now. The plus charge there, that's a secondary carbocation, which would be far more stable than if a plus charge was here on the end as a primary. Okay, so then let's see what's going on here. This and this lead to this. I think a new bond has formed here from this guy. Remember, there's electrons on the oxygen. This is going to get real important in chapter 14 because we're looking at oxygen molecules, functional group. So I'm going to propose that this bond forms from these electrons, because that's all a bond is, going to positive, forming that bond. There it is. Now, this oxygen only has one lone pair left, because this guy formed a bond. We're going to see lots of this in chapter 14. So this oxygen had more electrons here than it did here. So now it's a plus oxygen, and it's electron deficient relative. So if anyone is more curious about that, there's more to it than that. How did we get from here to the final? Which we knew from the start. We knew from the start we were going to add H and OH across the double bond. But how do we get from here to here? Water is still floating around here. So another water molecule can come and pull off one of these hydrogens, kick these electrons toward the plus charge, which is identical to what happened over here. And then that recreates the acid catalyst. Catalyst regenerated. We always talk about catalysts, but I haven't gone into too much of that yet. Catalysts help a reaction occur, but are not used up in the reaction. I'm sure that was covered in Gen Chem at some point. But but here we can see clearly how that happened. We had acid, it served as a source of hydrogen initially to add one of these hydrogens. And then it was regenerated in the end. So one other thing I'll point out is this process is reversible, which we're going to cover in chapter 14. So you can it's fine for this chapter 13 to remember that the alkene is hydrated in the way that we covered it up here. Here's the net reaction, alkene to addition of water across the double bond. Here we broke it out into steps. Really, my point of doing this is like, if you understood all this, then you really understand what's going on pretty well right now. Which bodes well for the future, because we're going to go more into some of this stuff. There will always be that fallback position of memorizing how a reaction goes. I start with this, and if I add this, I get this. That will always be worth points. But knowing more clearly what's going on in depth and breadth will help overall too. So another thing about organic chemistry is that we're not always given like, what do you get when you add this and this? In fact, when you think about it, the whole science of it is that we have something that we're trying to make. And really the question is, what do we make it from? What can we make it from? So can you fill in missing parts? This is a good test of understanding, right? So we know that we have an alkene here. It's very, very helpful to draw in implied hydrogens, at least the first dozen times you do it. So where are the implied hydrogens over here? Here and here, right? So that's why we covered structure and bonding and where hydrogens are so thoroughly in the first chapter, because it's so important to know that there's two hydrogens in a structure that's drawn like that. So what has been added to the alkene? basically H and I. So we know that we can add HCl, we know we can add HBr, we know we can add HI. Those are all in that one column of the periodic table, halogens. So when we first covered these reactions of alkenes, we mentioned this, I believe. So this is that reaction. Hydrogen adds to one, iodine adds to the other. So the missing part is just HI, as opposed to HCl, HBr, HI. So another good test, can you fill in, what if you had this and you were being asked this? You should be able to swap in components of these. Okay. So in the time left, I think, so now we've had 2 hours worth of alkenes for the most part, and reactions of alkenes. We did a little bit of aromatic compounds, mainly just their structures and simple names of them. So chapter 14 is going to be on alcohols, phenols, which is one of those benzene compounds. That's basically a special case of an alcohol, and ethers and thiols. And when I covered functional groups, these were all covered as like oxygen functional groups, or sulfur containing functional groups. Maybe this is connected to something, or an ether looks like this, for example. I covered these in the context of they're all single bonded molecules. So we're not looking at double bonded molecules in chapter 14 coming up. We're looking at single bonded. So this is phenol, as we learned at the end of the last video. It's an aromatic compound, and going back to the very beginning of today's session, we know that the ring is stable. And so therefore unreactive, relatively. Of course, anything can react if you give it strong enough conditions. That means that the reactivity is here. So at the beginning of the session, I was saying that we're going to focus, for aromatic compounds, we want to know how to refer to their names. But really, we're going to focus, as far as reactivity goes, we're going to focus on what's going on here, the groups that are attached to it. And a phenol is very much just a special case of an alcohol. So if we take a phenol or an alcohol and react it with a common strong base like sodium hydroxide, we remember from 111, this is what this really is a salt, essentially. Instead of sodium chloride, which is table salt, plus minus, it's sodium hydroxide, plus minus. So what's going to happen here is similar kind of chemistry to my more complicated example above, I guess. Electrons on oxygen, which make it negative, can go and form a bond to hydrogen, to the proton there. These electrons then move on to the electronegative atom oxygen, because hydrogen can't form more than one bond. And so the result of those bonds forming and breaking will be for any alcohol or phenol under these conditions, the oxygen of the phenol gaining electrons but losing a hydrogen, and the hydroxide ion picking up a hydrogen, and so it basically becomes water and it's no longer charged. So this is the nature of the reactivity of alcohols and phenols when you mix it with a base like this. This is a lot of the kinds of things we're going to look at in chapter 14. So instead of a phenol, I have an alcohol here. If I react it with OH minus, minus should bring to mind electrons. Electrons can form bonds. That it can form a bond to the hydrogen in the same way. These electrons can get kicked up onto oxygen, which makes sense because they're going toward a more electronegative atom. But just remember, these arrows are indicating bonds forming and bonds breaking. Bond forms, bond breaks. And because that's what the arrows mean, they form a system of explaining things. And I'm going to show you a common error that people do after this. So if we just follow the pattern that we saw just above, we end up with this and water. Of course, this can go on to react further in various ways, but right now I'm just covering it this way. The most common mistake, so if someone was presented this, most common mistake would be that for this to go to, I'm going to run out of room here. For this plus this to go to this plus this, people say this, they look at it and they say this hydrogen right here is going over here. So it's very tempting to say this hydrogen here is going here. That's where my arrow is going to point. But that's not what is happening. That's not what is happening with electrons forming or breaking bonds. In fact, when you think about it, you don't need that arrow. It's clear that that hydrogen went from there to there. Who needs an arrow to show you? It's like pointing it out even further, like just in case you don't believe, So it's not instructive particularly, but it certainly doesn't explain reactivity, because an arrow is meant to show the movement of electrons, whether it's electrons that used to be in a bond or electrons that were in a lone pair. These make sense in terms of chemistry, the science of chemistry. There's no science of chemistry here to just say this hydrogen goes over here. Can't you see? See, there it is. That won't help you explain anything, because by that logic, just to convince you further, if I had a molecule like this, which really doesn't even have a functional group, if by this logic I could say this hydrogen is going to go somewhere, it absolutely can't. That hydrogen is totally unreactive. So I think I went maybe a little too far in this explanation, but just to go back to this, the phenol reacts in this way, the alcohol reacts in exactly the same way. And so as a logical extension of this, thiols, so if you look at the periodic table, oxygen, is right above sulfur in the same column, periodic table. And what we learn in Gen Chem, hopefully, is that the columns show atoms that react and behave similar to each other as you go down. So oxygen and sulfur are pretty similar to each other. They both have 2 lone pairs, and sulfur can react in the same way, exactly the same way. So bond forms, bond breaks, leading to S minus and water. So again, if you're just memorizing things, this looks different enough because it's got an S instead of an O that you might have trouble, remembering if there was a whole bunch more of these different variations. But if you realize that they're reacting the same way on the same chemical principles, you don't really have to memorize this. That's sort of my take, the mechanistic approach to organic chemistry. In just the last minute or two here, and I'll leave some time for if there's any questions at the very end. Remember acid-base stuff from 111. So an acid is in the old sense of acids and bases, acids donate protons, right? That's what we learned first. Donate hydrogens. And bases accept hydrogens. That's the old Bronsted-Lowry acid-base stuff, right? So in this reaction that we're seeing right here, we know that sodium hydroxide is a base, and does it accept a hydrogen? It sure does. The alcohol then must be an acid because it donates its hydrogen. Its hydrogen's gone here. So this is an acid-base reaction. That's the Bronsted-Lowry acid-base reaction definition. So this fits that classical definition, Bronsted-Lowry. But there's the Lewis acid-base definition. Lewis acid accepts electrons. And Lewis base donates electrons. Sorry for squeezing this in some on the side here, but that also fits perfectly with what we're seeing here. Notice the acid that donated a proton is accepting electrons right here. Whoops. It's accepting these electrons right here. It doesn't matter that it's electrons from itself. It's accepting them. And then the base here, the OH, is donating electrons to form a bond, which is this bond right here. So it fits. The arrows go much more with Lewis acid base stuff. And in my opinion, Bronsted-Lowry acid base stuff should never, ever be taught again. Because it just gets people down that road of just saying, this hydrogen's going here and this hydrogen's going there. And it's like, that's not explaining a single thing. But I'm not going to be able to change that, unfortunately. But I'll emphasize the Lewis acid-base stuff, and that brings us right to 1050. And I want to see if either of you guys have any questions. Okay, I'm going to save this, and then the recording will be posted on the YouTube channel as usual. This YouTube channel right there, and I believe it's also in the side menu on Canvas under Panopto recordings. What I've learned is that Canvas itself can't hold the video for very long. It may not even be up there for a day, but because of that, it gets sent over to Panopto. So clearly the IT people realized that Canvas, doesn't have enough capability, and so they had to add on this other program. Canvas didn't have enough memory, to handle all the videos, especially after, in the pandemic times. So, but it will still be on I'll put it on the YouTube playlist right away. And then now we're moving into chapter 14. So look for chapter 14 things to start getting posted. But the quiz for chapter 13 will be posted around noon tomorrow. All right.
Thank you.
Thank you.
Thank you.
Have a good weekend as well. Okay, I'm gonna stop the recording now. So long.